Natural numbers, we defined addition, multiplication, and so on. I proved several properties of addition and assigned as an exercise to prove several identities involving multiplication and exponentiation. What I didn't do, which I promised like 2 lectures earlier, was to actually prove that 2 plus 2 equals 4 and 2 times 2 equals 4. I mean, we defined addition and we proved properties, abstract properties of these things, but we haven't actually used these in action. Now, how do you add 2? Obviously, I'm just doing this for fun, okay? Not that this actually matters, but why is 2 plus 2 equals 4? Let's actually understand this. Now, what is 2? This is the successor of the empty set, okay? Maybe I should write this with parentheses. Now, remember we defined addition so that addition satisfies 2 properties. The first property is that when you add 0 to an element, to a natural number, it doesn't change that number. M plus 0 is n for all m. And when you add successor of n to a number m, it's the same as first adding m to n, then taking the successor. So using the second property, you can actually show that 2 plus 2 equals 2 plus 1, and you take the successor of this guy. Now there are too many parentheses. I'm not going to now drop parentheses. Okay, I have this. So 2 plus 2 equals 3 plus 1. Now again, if you use this property, 3 plus 1 is 3 plus 0, and you take the successor of this. And now by the second property, 3 plus 0 is 3, so successor of 3 is 4. Successor of 0 is 4, okay? So you can actually prove that 2 plus 2 equals 4. Similarly, you can prove that 2 times 2 equals 4 and so on, okay? So you see, after 20-something years, you actually really know now why 2 plus 2 equals 4 instead of like probably in primary school just memorize this as a fact which came out of nowhere. It actually comes from these 2 properties. Anyway, let's leave that on the board. So this is actually how you prove that a certain equation like 5 plus 7 equals 12 actually holds using the properties of addition and multiplication. Maybe I should simply say definition, because this is how we defined addition, right? We said that we're going to define addition like this recursively, then prove that there exists such a operation by the recursion theorem. Anyway, that's that. I just want to do this because I had promised this earlier. Now let's talk about equinumerosity. Equinumerosity. Let me grab my notes. Okay. What's our objective? Our objective is to compare the size of sets, okay? We want to compare the size of sets. Obviously, if the sets you have are finite, whatever that means, we know how to compare them. Like, this is a set, this is the successor of 0, this is the successor of 0. We know how to compare it. We can come up with a way to compare these. This has 2 elements, this has 4 elements. I mean, I can count them, so I can say that this is bigger than this. Okay, that's fine. If I give you finitely many sets, whatever finite means, we already, like, without learning all about set theory, we already know how to compare sizes of those sets. If you have 2 finite sets, you simply count the elements. What if you have infinite sets? How do you compare the size of those? Now, one approach you can take is you can simply say that all infinite sets they're the same, they're of the same size. That's a perfectly nice notion of comparison, like that works. It works, unfortunately, it's not as useful as the notion of comparison we're going to develop. If you say that any two infinite sets are they're the same, they're both infinite, that's the way of comparing things, but that's not really useful. What we're going to do is we're going to use a shepherd's way to count things. What do I mean by shepherd's way? You have some sheep over there, okay, and you're supposed to take those guys to like big mountains, and you're going to bring those back because they're not yours. And you don't know how to count, you don't know natural numbers, you don't know how to count things. How would you make sure that you don't lose any sheep? What you would do is, you would probably grab a basket, you would take lots of stones, and for each sheep you would put in a stone into the basket. Then you would take the basket with you, and the sheep would eat some grass, and you're bringing those back. Now you're supposed to give the sheep back to their owner. What you would do is, for each sheep you give back, you're going to take one stone out of the basket. And at the end, you want to have no stones in the basket. Okay? Now, without knowing about natural numbers, without counting, you can actually make sure that the number of sheep you take to the mountains is the same as the number of sheep you take back. I said you're doing this without counting. You're going to probably object, I'm actually counting the number of sheep when I put in stones and so on. Yes, but you're not counting in the sense that you're not actually using the numbers. You're not using 0, 1, 2, 3, and so on. You're using stones to count the sheep. So what you're doing is you're using one set, you're using a set of objects to count another set of objects, okay? If you can do this, if you can just count objects in here, we are these objects, and these objects, we are these objects, we're going to say that, like, intuitively this should mean that the number of objects in these collections are the same, okay? So that's going to be our central definition. Two sets, A and B, are said to be equinumerous. They have the same size, okay? Being equinumerous means that they have the same size. If there exists a bijection between them, in which case we write this. Now you have two collections of sets. If there is a bijection between them, if there is a function which is 1 to 1 and onto from A to B, then for every element of A, you have a unique element of B, so that these are associated, these are linked. And for every element of B, there exists some element of A which maps to that guy, so they're related as well. If you have a bijection between them, what you're doing is you're basically labeling elements of B via elements of A. Or if you look at the inverse of this bijection, which is also a bijection, you can label elements of A via elements of B. If you can do this, this should mean that the size of A, whatever that is the same as the size of B, because you can just label elements of these collections with each other, okay, using each other. Now, you see, in this definition, I didn't use any number. So we don't really need the notion of a number to compare sizes of things. Okay, in order to compare the sizes, if you want to say that this collection of objects and this collection of objects are of the same size, they're equinumerous, you should just find a labeling of the elements of this guy via this set. So there should be a map, which is a bijection from this set to this set, or vice versa. Now, if two sets are equinumerous, we write this. Now we're going to ask the following question. Why are you using this notation? What does this mean? In future, this will mean the cardinality of A. So I'm going to use this notation again. I'm just preparing you for the notation that will come in a couple of weeks. So this will be a special cardinal number called the cardinality of A. We have not learned about it. For now, think of this as like a single big expression. If there's a bijection between A and B, we write this. Okay? Now, let's define what it means for a set to be finite. You see, while trying to motivate this definition, I kept saying like we don't have to use numbers. Like at the beginning I said if we have finitely many objects, then we already have an intuitive understanding of like the size of those things. We can compare these because we know numbers and so on. But do we really know what finite means? What is finite? We haven't defined it. We don't know what finite means. I mean, you know what finite means. Finite means finite. This is a finite collection of sets. But what is finite really? If you try to define finite in English, forget about mathematics, try to define finite in English or in Turkish, like in natural language, you will realize that you will have to use another concept which already somehow includes the notion of finite. You're going to come up with circular definitions. There is no way to define finite without mentioning finite. Well, there are ways, okay, but if you try to use the most obvious, intuitive, everyday definitions, you will see that your definitions are circular. Now we're going to define what it means for a set to be finite without creating some kind of loop. So it's not going to be a circular definition. We're going to define finite in terms of natural numbers. Okay? A set A is said to be finite if A is equinumerous with a natural number. If there is a natural number n such that A is equinumerous with n, meaning that there is a bijection f from one of the sets to the other. Okay? So in order to define finite, we use natural numbers. A set is finite if it is equinumerous with a natural number. Now, why is this not circular? Because, like, how do we define natural numbers? What's the natural number? It's the element of the smallest inductive set, which exists by axiom of infinity and so on. So, let's define what it means for a set to be infinite. A set A is infinite if it is not finite. Sets that are not finite are called infinite. Okay, now what's an example of an infinite set? I'm actually asking. Natural numbers. Why? Why is natural numbers infinite? How can you prove that the set of natural numbers, there's no bijection between the set of natural numbers and some natural number n? We're going to use the pigeonhole principle, which we're going to prove. Okay? Now, intuitively, this is a very simple question. What's the example of an infinite set? Natural numbers. Why? Because you can see that it's infinite, like it just goes on and on. But the reason this looks, the reason that the set of natural numbers is not finite looks obvious is because you're like thinking you're infinite in terms of our already developed understanding of infinite. Like it goes on and so on. However, if you use that definition, like a set is infinite if it is not finite, you want to prove, how would you prove that the set of natural numbers is infinite? You need to show that it's not finite. Now, what does finite mean? Finite means that it's not equanimous with a natural number. So you need to show that there is no bijection from the set of natural numbers to a natural number. That can be done, that's not difficult to do, but my point is proving this very intuitively obvious fact that the set of natural numbers is not finite requires some work if you use these definitions. And that's the price we have to pay, okay? If you try to define infinite with some informal, non-rigorous way, I'm pretty sure you can easily prove that the set of natural numbers is infinite using that non-rigorous, informal definition. But if you use this definition, there is some work to be done, which we're going to do today, hopefully. So let's go over what we have done so far. We defined what it means for two sets to have the same size. We defined what it means for two sets to be equinumerous. We then defined finite sets. A set is finite if it's equinumerous with a natural number. It's infinite if it is not finite. So what we're going to do next is the following. So we want to prove that the set of natural numbers is infinite. That's our first goal. We want to show that there is at least one infinite set. Before that, we need to first understand finite sets, how finite sets behave. So we're going to prove stuff about finite sets. Now, again, let me repeat this. We already have an intuitive understanding of the word finite and infinite. With your already developed understanding, what I'm going to state today, like the theorems I'm going to state today, they're obvious. For example, I'm going to state the union of two finite sets is finite. That's obvious, right? If this is finite, you put those together, that should be finite. Sure, like we can see this. This is obvious to us. However, if you use this definition, there is a little work to be done. So those facts which will read obvious when you see them, they're not really that obvious. Okay? So we defined finite sets, infinite sets. Now, let me state this lemma. For each n, for each natural number n, any injective function from n to n is surjective. Let's read this. What does this say? It says if you pick a natural number, so it contains 0, 1, 2, it goes up to n minus 1. If you have a function from the set to itself, which is injective, it has to be surjective. Why? Let's understand the reason. I'm going to map this guy to this guy, this guy to this guy, this guy to this guy, and so on. If this map is injective, then each guy in here is mapped to, like distinct guys in here are mapped to distinct guys in there. And now we're thinking that if that's the case, each of the elements in here, they get different labels. Well, this is the same set, so it's obvious, right? Like everything should be mapped by something because the number of the elements of these sets are the same. But you see, that's not a proof. Like, this is one of the things which is so intuitively obvious that you're thinking that like this requires no proof because it's obvious. Well, it's not if you use this definition. Sorry, yeah, it's not. This has nothing to do with this definition. Yes, this is obviously true, but this requires some proof. How are we going to prove this? This is a statement which starts with, for every natural number, something happens. How do you prove something about natural numbers? You use induction. We're going to do induction on n, okay? The claim is, I shouldn't really say vacuously true. It's clearly, no, it's actually vacuously true. Never mind. Vacuously true for n equals 0. Zero is the empty set. How many functions are there from empty set to empty set? How many functions are there from empty set to empty set? Not quite. None means that there are no functions. Exactly. There is only one function from empty set to empty set, namely the empty function. Now the empty function, this was one of the exercises. It's a surjection considered as a function from empty set to empty set. If you just consider this as a function from empty set to, let's say, this set, it's not a surjection. But if you consider it as a function from empty set to empty set, it is a surjection. It's a bijection, okay? Indeed, this is completely off topic, but I'm going to mention this. How do you define n factorials? You know, we define natural numbers, we can define factorials. There are a couple ways to define this. There's this recursive definition, or here's another definition. This is supposed to be the cardinality of bijections on the set N, okay? So this is supposed to be the number of elements in the set. How many bijections are there on the empty set? There's only one. So this set has cardinality 1. So this is why 0 factorial is actually 1. If you ask Al-Nasr about this here, for example, I mean, I know this because he's done this before. I'm not making up the name out of nowhere. It's going to tell you that, like, we have this recursive definition. We define 0 factorial to be 1. That's one way to go. If you just go with the recursive definition, that 0 factorial is 1. It's just part of the definition. If you go with this definition, it is a theorem that 0 factorial is 1 because there's only one bijection on empty set. Anyway, this was completely off topic. Let's go back to what we were doing. What were we doing? We're doing an induction. We did this. We said that the claim is vacuously true for the empty set. Now assume that now let n be a natural number and assume that the claim holds for n. You see, in the previous lectures, when I did induction arguments, I was doing this. Let I be the set of all natural numbers satisfying blah, blah, blah. Then we're going to prove that I is inductive. I was doing this so that, well, I was only doing this because that's the correct way of doing induction. Because what's the principle of induction? It says that any inductive subset of natural numbers is all of natural numbers. And in order for that principle to fit the proof we were doing, I had to just introduce that set and prove that this set is inductive, therefore it's the whole thing, therefore what I claim is true for all natural numbers. From now on, I'm just going to do the induction the way you were already doing before taking this class, okay? So this is true. The claim is true for 0. Assume that it's true for n. We wish to show the claim holds for successor of n. Now, let's go to this board. How do you show that this claim is true for successor of n? You need to show that any injective function from successor of n to successor of n is a surjection. So let f be an injective function. Okay? Assume to the contrary, we want to prove that this injective function is a surjective function. Assume to the contrary that this is not surjection. Contrary that, or maybe I should write it here. Assume to the contrary that f is an injective function which is not surjective. So assume that the claim does not hold for successor of n. And there are two cases. The first case is this is not a surjective function, right? What does not surjective mean? It means that one element in the codomain is not mapped to. Now there are two possibilities. This n might not be like the image of this function might be contained over here, okay? This might not be in the range, okay? This is one possibility. Now, if this is the case, if this little n is not in the range, then if I restrict this function to little n, I'm going to grab this chalk. If this little n is not in the range, what I'm going to do is I'm going to restrict my attention to these guys. I'm going to restrict this function to n. Then, I don't know where this goes. This will be an injective function. Why? Because if you restrict an injective function to some subset, you still get an injective function. Well, maybe I should erase this because I'm going to change something. So then this is an injective function from, okay, what's the domain of this function? It is n. What's the range of this function? It's still, sorry, it's a subset of n, okay? This still goes to, like, if you just map these guys via f, they still go to some value which is different than n, so the range is a subset of n. What's the domain E? What's the range of this guy? The range of this guy is different than n. Why is this the case? Because, you see, the range of the whole thing is contained in here. So, in particular, this little n, it's mapped to some guy over here, f of n. So, if I restrict my function to these elements, if I just get rid of n, the range of the restriction, it can't be all of n, okay? Indeed, it's just, it has to miss this guy, f of n. So this element, f of n, is mapped, like, n is mapped to f of n, and this is an injective function, which means that if you restrict your function to these guys, if you just don't look at the image of this guy, then this guy, this f of n, cannot be in the range of this restriction. In particular, we have the following. I'll look at the restriction. The range of the restriction cannot contain f of n. This contradicts that the claim holds for n. Why? This is a function from n to n. It is injective, but it is not surjective. Okay? So there, I just construct the function from n to n, which is injective but not surjective. That contradicts the induction assumption. Okay? So this is the easy case. If n is not in the range of this function f, then just simply by restricting this, I can found an injective function which is not a surjective function from n to n, and that contradicts the induction assumption. Now, let's focus on the second case. If n is in the range of f, then, now the picture is going to change, and I'm going to move over that board, but before that, let me do this. Then, there is some k mapping to this guy for some k in S of n. Okay? That's by definition. If this is in the range, then there is some k in the domain which maps to this. Now we're going to play with, we're just going to modify the function a little bit so that we again contradict the induction assumption, okay? So let me draw a picture over here. S of n, 0, 1, 2, dot, it goes up to n. 0, 1, 2, dot, it goes up to n. Now, this is the picture in the second case. I have a function f, and the image and the range contains n. So this is in the range, which means that there is some k mapping to this guy. Again, we're going to have two subcases. Case 1, I can be lucky. Maybe I'm lucky. This k, which maps to n, is actually n. In this case, again, if you restrict your f, if this k is n, if you restrict your f to n, just like over there, so you don't look where this goes, it goes to n, you will have an injective function which is not a surjection. This is an injective function from n to n, which is not a surjection. Okay? Contradicting induction assumption. Okay? Induction assumption. Why is this not a surjection? Because, you see, this is in the range. There is supposed to be some element which is not in the range. Well, it can't be this guy, so there has to be some guy over here which is less than n, which is not in the range. But then if you look at the restriction of this function, you find an injective function whose range does not contain that guy, so we contradicted the induction assumption. Case 2, let's say that k is not n. So this guy, this k, which maps onto n, is something different than n. Here's what I'm going to do. Then the relation, okay. Let me write this down first, and I'm going to explain what's going on later. This relation is an injective function such that if k is not n, here's what I do. I take my function. This maps k to n. Now, I take that pair, I take that ordered pair out. So now it does not map k to n anymore. I'm going to modify this f to some g. What I do is I take this out, so it does not map k to n. And it maps n to f of n. Okay, this n goes to some f of n. And I take this pair out as well. So the domain of my function is now n. Okay? And I add the following. K is mapped to f of n. So if k was mapped to n, I deleted that arrow, and n was mapped to f of n, Now what I do is I delete that arrow as well. Now I'm mapping k to f of n. So this is now free. You see, this was mapped to this guy was mapped to this guy was mapped to this guy. I'm just going to delete those arrows and map this guy to this guy so that this is now free. So it's not in the range as well. Now this guy is an injective function from n to n because I got rid of this n as well. This is an injective function from n to n such that you can easily check simply by this equality that the range of G is the same as range of f, okay? Range of f, except the last guy I deleted, n. Now, yes, the range of G is the same as range of f except n, okay? Pictorially, it should be obvious. You can double check this using the definition of range if you just use this equality. Now, since range of f is, it's not the whole thing because we assumed that f is not surjective, there is some k in the range of, oh, sorry. Since the range of f is not the whole thing and n is in the range of f, you see before I erased this, n was in the range of f, we have that there is some k in n such that k is not in the range of G. Previously, I had this picture, this was S of n, and I had this range of f. I just modified this function a little bit. I got rid of this guy. Now, the range of f was not all of S of n, but this n was in the range of f. So whatever is missing in the range of f, it's not n, it's some other element. Okay, so there is some element less than n which is missing in the range of f. But because of this, it's automatically missed in the range of G. And now I have an injective function from n to n which is not surjective. The existence of G contradicts the inductive assumption. Okay? Now, so in all cases, we end up getting a contradiction, which means that the assumption we made at the beginning that there's an injective function from S of n to S of n which is not surjective, that has to be wrong, okay? And that finishes the proof. If this is wrong, then any injective function from S of n to S of n is surjective, but then that's what we wanted to prove. That proves that the claim holds for S of n. Now, this lemma has an obvious consequence, which is known as the pigeonhole principle. Okay? Corollary, the pigeonhole principle. The pigeonhole principle tells you the following. If you have two natural numbers such that m is strictly less than n, then there is no injective function from the bigger guy to the smaller guy. Okay? And the proof is clear. Assume not. assume towards a contradiction that, so in order to get a contradiction, assume that this is not true. Towards a contradiction that there are natural numbers mn such that n is greater than m, such that there's an injection from n to m, okay? So assume that this is not true. So there are natural numbers mn such that n is greater than m, and there's an injection f, let's name this f, from n to m. Then, if you restrict your function to m, you see f is a function from n to m. This is bigger than m, meaning that m is a subset of this guy. So I can restrict this function to m. And now this is a function from m to m, is an injective function. This is an injective function which is not surjective. Okay? Because if you restrict an injective function, you're still going to get an injective function. By restricting it, you can't possibly make the range bigger, but the range already missed at least one element in here. It's not all of them, so it's still not all of them when you restrict it. So it's an injective function which is not surjective. This contradicts the lemma. Okay, this is one of the corollaries of the lemma we proved, the pigeonhole principle. Have you seen a proof of this before in the first year? No, you mentioned this, I know that, but have you proved it? Have you proved it? No? Okay, the proof is by induction. And actually, you can see that it's like, the whole proof is actually done within that lemma. There was this there's a website called Math Overflow where professional mathematicians ask each other like questions, sometimes fun questions. Someone asked like, can you tell me, like list the examples of difficult theorems with trivial proofs? And someone wrote, for some reason, pigeonhole principle, because he was thinking about the proof. And Timothy Gowers, the famous mathematician, you can look him up, his work, he said, look, you see, some consider this as a trivial theorem with a difficult proof. And I totally agree with that point. Like, this is obvious. This guy has more elements than this guy. If you try to come up with a labeling from the bigger guy to the smaller guy, if you try to label the elements of the smaller guy with the bigger guy, you will have to just label the same object with two different labels. That's obvious. But if you actually try to prove it, you have to do a long induction argument, which is not conceptually difficult, but it's tedious to write it down. It's tedious to write down. Anyway, another corollary is, this is a corollary to the lemma, not to the corollary to the corollary. The set n is infinite. The set n is infinite. Okay? Now, why is this the case? There is a function, the function f from natural numbers to natural numbers, which sends little n to successor of little n, is an injection which is not a surjection. If the set of natural numbers were equinumerous with some natural number k, say this G is a bijection, say that you found a bijection between natural numbers and some natural number, set of natural numbers and some natural number. Then, yeah, I have to get this correct now. I want to find a function from k to k, which is an injection but not a surjection. So I have to apply G inverse, then I have to apply F, and I have to apply G. Okay. We have a function on natural numbers which is an injection but not a surjection, namely the successor function. Pretend that there is a bijection between the set of natural numbers and this natural number k. Then if you look at the function G composition, F composition, G inverse, this is going to be a function from k to k. And this will be an injection which is not a surjection. Contradicting the lemma. Why is this the case? We assume that this f is not a surjection. So its range is not all of n. It misses some element. Which element do you want it to miss? Let's say it misses 7 over here. 7 is not in the range. If 7 is not in the range, then g of 7, which is an element of k, is not in the range of this guy. So if you are missing some element m here, if m is not in the range of f, then g of m, which is an element of k, is not in the image of, it's not in the range of this guy. However, these are all injective functions. Composition of injective functions is injective. So this is an injective function which is not a surjection, and it's from k to k. This contradicts the lemma. Okay? So the set of natural numbers is infinite. Okay? See, proving this, like, it took a lot of work, right? It's intuitively obvious, but we had to do a lot of work. More specifically, we had to prove that from a finite set to itself, every injection is a surjection. Anyway, so we proved that. Now, we're going to prove more things about finite sets. We're going to prove that subset of a finite set is finite, union of two finite sets is finite, and so on. And I think after that, we're going to be done with today's lecture. Next Tuesday, we're going to start talking about infinite sets and countable infinite sets and so on. But today, we have to finish the stuff about finite sets. So let's have a 10-minute break. Be back here at 12:41.